Students, do revision on Model 5, that is ideal gas mixture and real gases. In the previous class, we discussed with real gas problem. Okay, so please do remember the real gas equation is given by Van der Waals equation, that is P plus A by V square into V minus B equals to RT. So where P is pressure of the gas, okay, and V is specific volume. In terms of specific volume, suppose if you are going to express in terms of meter cube per kg, uh, and one more is there, that is meter cube per kg mole. In that case, you have to multiply uh, the specific volume by molecular weight. Screen is visible, students. Is it visible? First, you should know the definition of ideal gas. Ideal gas or perfect gas is the one which is having no intermolecular forces of attraction or repulsion. Okay. During thermodynamic process, an ideal gas does not change its phase and follows the gas laws at all ranges of pressure and temperature. Okay. So remember, ideal gas is the one which is having no intermolecular force of attraction or repulsion. The intermolecular forces of attraction and repulsion intermolecular force of gas, okay, whereas attraction or repulsion are taken into consideration. An ideal gas does not change its phase, okay, whereas the real gas is the one which changes its phase, and the ideal gas follows the gas laws at all ranges of temperature and pressure. Okay. On the other hand, the real gas is the one which obey the ideal gas laws only at particular condition. So especially at the elevated pressure and temperature, uh, at low pressure or at high temperature. Okay, so tends to follow the ideal gas laws only at low pressure condition and high temperature condition, or at both conditions. Okay, and we studied the Boyle's law. Okay, Boyle's law. So before deriving, we are having a derivation called as characteristic gas equation. Okay, before that, you should have the idea of the Boyle's law, Charles law. Once you know this Boyle's law and Charles law, we can easily do the derivation of characteristic gas equation. Okay. Ideal gas equation or characteristic gas equation, which is given by PV equals to MRT. We use this equation while solving the numerical problems. Okay. P is pressure of the gas, V is volume of the gas, M is mass of the gas, R is general gas constant. Remember, R is difference of Cp and Cv, specific heat at constant pressure and specific heat at constant volume. and the value is 0.287 kilojoules per kg Kelvin for air. The first one is Boyle's law. It states that during a process, the volume of the gas varies inversely with pressure when the temperature of the gas kept constant. The volume is inversely proportional to the pressure of the gas when temperature is kept constant. We studied the expansion process and compression process. Okay, so in case of the expansion process, as the pressure increases, as the pressure decreases, the temperature decreases, volume increases, and in case of compression process, the pressure increases, the temperature increases, and volume increases. So there will be inversional proportionality between the volume and pressure of the gas when temperature of the gas is kept constant. P is proportional to 1 by P when temperature of the gas is kept constant. Or PV equals to constant. Okay. For different state points, we studied state points in first chapter, that is introduction chapter. State point is the one which is having the definite the values of properties. For example, P1, V1, T1. Suppose if you are taking the process between the two stage points P1 to 2, in that case we are having the final properties as P2, V2, T2, etc. So Boyle's law states that whenever temperature is kept constant, the volume of the gas is inversely proportional to the pressure. And second one is Charles law. So we are having the two forms of Charles law. During the change of state, the volume of the gas is directly proportional to the temperature when the gas is maintained, when the pressure of the gas is maintained constant. Mathematically, we can write V is proportional to T when P is kept constant, or mathematically we can write V by T equals to constant. So if you are taking for different state points, we can write V1 by T1 equals to V2 by T2 equals to Vn by Tn. That is equals to constant. Next, Charles law also stated as during the change of state, the pressure of the gas is directly proportional to the temperature when the volume is maintained constant. There are two forms of Charles law. Two forms. Okay. The pressure of the gas is directly proportional to the absolute temperature when the volume of the gas is maintained. So P is proportional to T at V equals to constant, or P by T equals to constant. So these are the two forms of Charles. Okay, now we'll derive the characteristic gas equation or equation of state or perfect gas equation. Okay, so they used to ask derive the expression for characteristic gas equation or ideal gas equation. So first we have to draw this PV diagram. Okay, PV diagram, and we are having this curve, and there are three state points. Okay, 1, A, and 2. Okay, so we can take directly from state point 1 to state point 2. It is a thermodynamic process, and we can take from process 1 to A and A to 2. So these are the two paths for the process 1 to 2. 1 to 2 directly, and another path is 1 to A and A to 2. 1A is constant pressure process, and A to 2 is constant volume process. Okay, so before deriving any expression, for example, find out the expression for work done during polytropic process, in that case you have to draw the PV diagram. Okay, PV diagram and TS diagram play a very important role in thermodynamics. You should have the idea of PV diagram and TS diagrams. So we'll have the TS diagram in the entropy chapter and in the second of thermodynamics chapter. Okay, so PV diagram mainly in case of module 1 and module 2. The characteristic equation already we studied, that is PV equals to MRT. This gives the relationship between pressure, volume, and temperature of the gas. Okay. This equation can be obtained by the gas law. Now consider PV diagram which represents change of state of gas as shown in the figure. Okay, consider two state points 1 and 2. The change of state from 1 to 2 can take place by following the path 1 to A and A to, and the properties are independent of the path followed. As I said, we studied point function and path function uh, in module 1 and module 2. Anybody, what is the difference between point function and path function? What is the difference? Okay, so we come across point function and path function. Point functions are the thermodynamics properties, and all the thermodynamics properties like pressure, volume, temperature, enthalpy, entropy, internal energy, all are the point functions. On the other hand, we are having the path functions. The path functions are the work done and heat transfer. Okay, they do not depend upon the end state points, rather than they depends upon the entire path followed during the change of state. Okay, and all the point functions or thermodynamic properties are the exact differential. For example, integration of dv we can write it as v2 minus v1. Integration of a dp we can write it as p2 minus p1. Like that we can write, but we cannot write integration of dw as w2 minus w1, because work done and heat transfer are the path function. They do not depend upon the end state points, rather they depends upon the entire state path followed during the change of state. Okay. And we can represent the work done and heat transfer as a w1 to 2 and q1 to 2. Okay. Now we have to apply the law, Charles law, for the process. Now, first you take only the one process, that is 1A. 1A is constant uh, pressure process. As I said, for constant pressure process, the volume of the gas is directly proportional to the temperature when pressure of the process remains. We can write, we can take the two state points 1 and A. V1 divided by V1 divided by T1 equals to VA divided by T. Consider process 1A, that is constant pressure process. V1 divided by T1 equals to VA divided by TA, or TA equals to T1 into VA by V1. So TA equals to T1 into, you see the diagram, the A and 2. The process A and 2 is the constant volume process. So VA and V2 values are same. So we can replace VA by V2 and you keep V1 as it is. So from this expression, we are going to find out TA. TA equals to T1 into VA by V1. So TA equals to T1 into V2 by V1, or VA equals to V2. Now we have to apply gas law, that is keeping a volume. We are going to consider the process V2. So P by PA equals to P2 by T2. So how we are writing the equation for process 1A, like that we can write the expression for the process A2. That is PA divided by TA equals to P2 by T2. Okay. That is PA divided by TA equals to P2 by T2. Now, once again, from this equation, we are going to find out the value of TA. Value of TA is given by PA divided by P2 into T2. Now, you see the process. PA is equals to P1. So, PA equals to P2. So, PA equals to PA divided by TA equals to P2 by T2. From this equation, we are going to find out the value of TA as PA divided by P2 into T2. But from the PV diagram, it is clear that process A2 is constant volume process. We can write PA equals to P2. So we have to replace PA as P2. From this equation, we can write sorry, PA and P1, P1 are same. So we can replace PA as P1. So TA equals to T2 into P1 divided by P2. So you call it as equation number 2. Now you compare the equation number 1 and 2. So on the left hand side we have TA. Okay, on the right hand side we are having T1 into V2 by V1 and T2 into P1 by P2. Now we are going to compare the equations 1 and 2. Okay, so we can write T1 into V2 by V1 left hand side equals to T2 into P1 by P2. So we can write this T1 V2 divided by T1 equals to P1 T2 divided by P2. Now you take the P2 as the numerator of this equation. We can write P2 into V2 divided by, you can take T2 as the denominator of this equation. T2 V2 divided by T2 equals to, you can take the V1 as the numerator of P1 and T1 as the denominator. So we can write P2 V2 divided by T2 equals to P1 V1 divided by T1. So this is the equation holds good for two statements 1 and 2. Suppose if there are n number of statements, in that case we can write this equation as P1 by P1 V1 divided by T1 equals to P2 V2 divided by T2. So, and this is equals to some constant R. So V by T equals to R, where M is the mass of the gas. One more thing here, volume is we are going to express in terms of V equals to small m into V. M is mass of the gas, it is in kilogram, and small v is it is meter cube per kg. This kg gets cancelled, we will get in meter cube. So specific volume is always given by the volume of the gas divided by mass of the gas, and unit of specific volume is meter cube per kg. How we are having specific volume? We are having a specific internal energy, then specific mass, etc. Okay, specific internal energy is kilojoules per kg. Like that, whenever you are going to divide any thermodynamic property by mass of the gas, in that case we are calling it as specific term. Okay, specific volume is the volume divided by mass, meter cube per kg. This is P into small v divided by T equals to R. Okay, that constant is represented by R, and small v is nothing but capital V divided by M. Now we are going to substitute the value of small v as capital V by M. In above equation, we can write it as PV equals to MRT, where M is the volume of the mass, it is in meter cube, and R is the general gas constant. Okay. So PV equals to MRT. This is the equation. This equation is known as the ideal gas equation. So in the exam, suppose they ask, first you have to write the PV diagram, write the equation, okay, and then finally you arrive the equation PV equals to MRT. So this is the one standard equation we are using everywhere for thermodynamic process, and this equation is known as the characteristic gas equation or the state for a perfect gas. Okay, and you remember the is ideal gas equation which follows all ranges of pressure and temperature. Okay. And yesterday we studied real gas. Real gas is the van der Waals equation, that is P plus A by V square into V minus RT. And you see the general gas constant, the value of the general gas constant for different gas, but you remember only for air. Okay, that is standard gas is air. That is uh, is 0.287 kilojoules per kg Kelvin. And one more is there, that is universal gas constant. Universal gas constant is uh, it is represented by symbol R bar, and relationship between R and R bar is R equals to R bar divided by M. Okay. R is universal gas constant, that is always represented as 8.314 kilojoules per kg Kelvin divided by molecular weight gives the general gas constant. Okay, and we are having certain laws in ideal gas. Okay, one law is the Avogadro law. Okay, the Avogadro law states that the equal volumes of all gases at same condition of pressure and temperature have the same number of molecules. Okay, so whenever they ask, write the Avogadro's law states that the equal volume of all gases at the same conditions of pressure and temperature will have the same number of molecules. Next, we are having one more important law called as Dalton's law of partial pressure. Okay, that is the sum of all individual partial pressure equals to the total pressure of the gas. That is the Dalton's law of partial pressure. Okay. Now I'll prove one expression, that is internal energy. Internal energy is a property we studied in first law of thermodynamics. Okay, the expression for first law of thermodynamics is Q equals to delta U plus W. Q is the heat transfer, delta U is change in internal energy, and W is the work done. Okay, and delta U is always final internal energy minus initial internal energy. Like that, we're having delta P equals to P2 minus P1, delta T equals to T2 minus T1, delta H equals to H2 minus H1. Like that, the change in internal energy delta U is the U2 minus U1. Remember the property, and internal energy is also the property, and it is always depends upon the temperature. Okay, and it is given by Joule's law, and the standard formula we discussed in the first law of thermodynamics is delta U equals to mCV into delta T. This is the standard equation used for all the process. Okay, so delta U equals to mCV delta T holds good for constant pressure, constant temperature, constant volume, isotropic and adiabatic process. Now we have to prove the internal energy and enthalpy are the functions of temperature. It depends only on the temperature. They do not depend upon any other parameter. This is the proof. Okay, now we know that first you have to write the first law of thermodynamics. First law of thermodynamics, Q equals to delta U plus W. And in differential form, okay, see, this is the differential form of first law of thermodynamics. dq equals to du plus dw. So before that, first you write the first law of thermodynamics, that is q equals to delta u plus w, and dq equals to du plus dw. And dq is tds. How you're getting dq equals to tds means, okay, that ds equals to dq by t. Remember, the entropy of any substance is given by ds equals to dq by t. So dq is nothing but the td. Okay, so don't write directly this equation. First you have to write first law of thermodynamics, that is q equals to delta u plus w. The differential form of first law of thermodynamics is dq equals to du plus dw. dq is nothing but t into ds. How we're getting this? ds equals to dq by t, or dq equals to t into ds, and du put as it is, and the displacement work is always given by p into dv. Remember, it's a formula for the work done. Okay, so tds equals to du plus pdv. Now we are going to divide throughout by t. ds equals to du by t plus pdv divided by t. So for this equation, we are going to divide throughout by t. What you'll get after dividing t? T gets cancelled. You will get ds only, du by t plus pdv by t. So dividing throughout by t, we get this expression. And you remember, the internal energy is function of temperature and volume only. So U equals to function of TV. U is internal energy. It is function of T and V. So, and in terms of partial derivative, we can write this expression as du. Okay, this U is function of T comma V. Whenever you are writing in terms of partial derivatives, we can write this expression as du equals to del u divided by del t uh, into dt, keeping volume as constant, and in the next term we have to keep the temperature as constant and variation of u with respect to v. Okay, how we are going to write? Del u divided by del t into dt whenever volume is kept constant, plus del u divided by del v into dv, temperature is kept constant. So this is how to represent the partial derivative equation. Now we are getting this expression du as del u divided by del t into dt whenever volume is kept constant, plus del u divided by del v into dv whenever temperature is kept constant. Now substitute the value of du in the above equation. So ds equals to, substitute the value of du as del u divided by del t into dt plus del u divided by del v into dv in the above equation. So ds equals to 1 by t. Okay, same thing. So 1 by t put as it is, and d is, you have to substitute this value. Okay, del u divided by del t into dt plus 1 by t into del u by del v into dv whenever temperature is kept constant, and you write the third term as it is. Here we are going to replace du by this term. Okay, next, so among this equation, find out what are the terms are common. Okay, so here uh, 1 by t is common for all the three terms. You take 1 by t, okay, 1 by t in the bracket del u by del t into dt plus 1 by t del u by del vt plus p. Okay, so p by d is multiply by dv. Okay, Now here, first term you write as it is, that is 1 by t del u by del t into dt, and second and third term you take 1 by t as the common, because 1 by t and dv is the common in the second and third term. So 1 by t in the bracket del u divided by del v plus p. So you write first term as it is. In the second and third term, take 1 by t as the term, del u divided by del v plus p into dv. So you call it as equation number 2. And one more is there, that is entropy. We studied the concept of internal energy in first law of thermodynamics. Like that, we are going to study the concept of entropy in second law of thermodynamics. That is S equals to F of T comma V. Okay, once in how the internal energy is function of temperature and volume, like that entropy is also the function of temperature and volume. So ds equals to same thing. How you are writing, we have to write like same thing, that is del s sorry delta s divided by delta t into dt, that is delta sorry del s divided by del t into dt, keeping volume as constant, plus del s divided by del v into dv, keeping t as constant. How we are writing for internal, the same thing we have to write for entropy also. The entropy is represented by symbol s. Internal energy is represented by symbol u. The enthalpy is represented by symbol h. So ds equals to del s divided by del t into dt plus del s divided by del v into dv. So you call it as equation number 3. And we have to write, we have to compare the equation number 2 and 3. So comparing equation number 2 and 3, so we can write, you see, compare. So the left hand sides are same. Okay, in the right hand side we have to equate. Okay, that is 1 by t del u by del t is equals to this term. You see the first term in equation number 2 and 3. So 1 by t del u by del t equals to del s by del t, and next we have del s divided by del v t equals to this term. Okay, so the first term dt is common. You can write del s divided by del t v equals to 1 by t del u divided by del t, and in the second term, that is del s divided by del v at constant temperature equals to this term, that is 1 by t del u by del v. Just you compare equation number 2 and now you consider equation number 4 and 5. Differentiating equation number 4 with respect to v and keeping temperature as constant. So differentiate equation number 4 with respect to v and keeping temperature as constant. We can write del square s divided by del t del v. Okay, so differentiating equation number 4 with respect to v. Okay, so del square s divided by del t into del v equals to 1 by t del square u divided by del t del v. Similarly, so differentiate equation number 5 with respect to t. With respect to t, how you are getting means del square s divided by del v del t equals to the differentiation of this term with respect to t is given by 1 by t del square u divided by del v del t. So 1 by t del square u divided by del v del t plus 1 by t uh, del p divided by del t keeping as constant and minus 1 by t square uh, del u divided by del v minus p by t square. Means first you have to differentiate this equation keeping one term constant and differentiate this. We can write minus 1 by t square into del u divided by del v minus p by t square. So this is the after differentiating the equation number 5 with respect to t, we'll get this. So remember this equation they may ask for the 8 marks question. Okay, so you have to practice. Now comparing equation number 6 and 7, we can write here the left hand side are same. Okay, then you have to equate the right hand side. Okay, so after comparing the LHS and RHS, we can write. So anyhow LHS are same, just equate the RHS term. That is 1 by t del square u divided by del t del v equals to 1 by t del square u divided by del v del t plus 1 by t del p by del t minus 1 by t square del u divided by del v minus p by t square. So you see the cancel. These are the same term. We are going to cancel on LHS and RHS side because these are same. And remaining thing we can write it as and divide multiplying throughout by t square. Okay, for this equation, what you are going to get. Okay, so whenever you are going to multiply this equation by t square, here t square divided by t, what will get t into del p by del t. Remember here we are going to multiply throughout by t square. That is t square divided by t is t into del p by del t equals to you shift this term towards RHS LHS side, that is del u divided by del t means multiply by t square by t square is 1. So we can write del u divided by del v plus p, that is minus p by t square into t square is will get minus p. When you shift towards left hand side it becomes plus. So you can write multiply throughout by t square and rearrange the terms. U divided by del v t plus p equals to t into del p by del t v. Now for ideal gas, we know that just now we derived the expression for ideal gas equation is given by PV equals to RT. Okay. And we have to differentiate P with respect to T. Simple differentiation, we can write it as V into del P by del T equals to R into del T by T means 1. Differentiating with respect to T, keeping volume as a constant. Okay, for this equation, differentiate, simple differentiate with respect to T, keeping the volume as constant. Whenever keeping the volume as constant, we can write like this: V as it is into dP by dt, keeping volume as constant, R into dt by dt. That means you get 1. That's why not writing that one into 1. So you can write uh, del P divided by del T or dP by dt equals to R by U. You can take the V as the denominator of R. We know that PV equals to RT. So R equals to PV by T. Now, so you see, substitute the dP by dt is this is the equation what we got. Del U divided by del V plus P equals to T into del P by del T. Okay. So now you substitute the value of del P divided by del T as P by T in above equation. Okay, so don't change the LHS equation, you put as it is. This is del U divided by del V plus P as it is and T as it is. But del P by del T is nothing but our P by T. So replace this term with P by T. So PP gets cancelled. LHS and RHS, T and T gets cancelled. We get del U divided by del V equals to 0. Now, similarly, del U divided by del P is also 0 whenever you keep the temperature as constant. Okay. After integrating, we'll get integration of du equals to integration of 0. It is nothing but u equals to constant. Hence, this is called as Joule's law. It is the function of temperature. But so u equals to f of t. It is only for ideal gas. That is uh, del u divided by del v equals to 0. So after integration, integration of d equals to integration of 0. That is u equals to constant. Hence, we can say that internal energy is a function of temperature. It does not depend upon any other parameter. Now, the enthalpy, as I said, enthalpy is also a function of temperature only. You remember this is a standard formula for enthalpy. Enthalpy equals to U plus PV. That is, this is a standard formula for enthalpy. Okay. That is H equals to U plus PV, U plus RTL. So we can write, because in this case, as internal energy is a function of temperature only, hence we can say that enthalpy is also a function of temperature only, because already we proved the internal energy is a function of temperature, hence the enthalpy is also the function of temperature only. Next we are having the specific heat. Okay, specific heat is the amount of heat required to rise the unit mass of the substance to unit degree rise in the temperature. Okay, so H equals to U plus RT. How we are getting H equals to U plus RT means H equals to U plus PV. PV is nothing but RT. H equals to U plus RT. Now in the differential form, we can write it as dH equals to du plus R into dt, where R is the constant. We cannot write dr, so we can write as dH equals to du plus R dt. And dH, how we are having du equals to Cv dt, that dH equals to Cp into dt. And du is always given by Cv into dt. You should remember these two formula. dH is always Cp into dt. Du is always Cv into dt, and you put R into dt as it is. Okay, so Cp into dt equals to Cv into dt. dt is nothing but the change in temperature plus R into dt. So dividing throughout by dt, we'll get Cp equals to Cv plus R. Okay, R equals to Cp minus Cv. We know that uh, uh, gamma specific heat ratio of specific heat is given by Cp by Cv equals to gamma. Okay, R is Cp minus Cv. Cp is nothing but gamma into Cv minus of Cv. R equals to Cp minus Cv, gamma into Cv minus of Cv. Okay. So R equals to, you take Cv as the common term, gamma minus 1. So from this equation, we can write Cv equals to R divided by gamma minus 1. And Cp equals to uh, gamma into Cv. So gamma into R divided by gamma minus. And Cv equals to R divided by gamma minus 1, and Cp equals to gamma into R divided by gamma minus 1. The expression for Cp, Cv, and gamma. So in this case, this Joule's law is most important. We used to ask, prove that internal energy is a function of temperature only. The enthalpy is function of temperature only. Okay. So how we are getting R is Cp minus Cv, and one more equation is there that is called as gamma. Gamma will come across in adiabatic process. Adiabatic process is the one where no heat transfer takes place between system and surroundings, and it is given by PV raised to gamma equals to constant. So we are having R equals to Cp minus Cv. So Cp is nothing but gamma into Cv minus Cv. You take Cv as the common, gamma minus 1. So Cv equals to R divided by gamma minus 1, like that. So you have to remember this equation. R equals to Cp minus Cv, gamma equals to Cp by Cv, PV equals to MRT ideal gas equation. Okay. So dear students, hope you understood this Joule's law. Okay. Now the important expression. Those who are, so please enter your USN in the chat box. Attended the class. Please, all of you enter. All of you enter your USN in the chat box for attendance. Okay, any doubts, guys, relating ideal gas, real gas? Any concepts you have not understood? Okay, I'll stop the session now.